Alrighty, good morning, guys. Can you hear me?
Yeah.
How are we doing? Are there any questions before we get started on today's material?
Can you go over the homework question? It was about the joint density. Hold on, I could pull it up if you don't remember.
Was it in the last homework?
Yeah. It was
7. Yeah, let me bring it up.
It was problem 1, 2 is compute the
Okay.
joint density of XU or X and U independent Y not.
Yeah, it's this one here, right?
Yeah.
So the reason I put the problem there was to highlight this, that if you want to say something about a two-dimensional random variable, one needs to work with joint densities. Knowing the marginal densities in general, this is not sufficient to know what the joint distribution is. Unless you have special properties such as independence. But if you don't have independence, then you need to know the joint distribution. It's insufficient to just know the marginals, right? So if you know the marginals of X and U, you cannot, in general, say anything about what the joint density is. The other way around is okay. If you know what the joint density is, then from the joint density, you can recover the individual densities. So that's why I put the problem on there, because it can seem confusing that you can know what is the distribution of X and what is the distribution of U, but you cannot know what the joint distribution is. That requires a lot more work. Okay, so that's why I put it on there, so we can try to dig into this. What is it then that you should or could do to get the joint density? Okay, does that make sense?
Yeah, that makes sense.
It can just be deceiving, right? Because very often when you see random variables, then you will look at the distribution of y1 and the distribution of y2 and y3 and so on. But then if you look at the distribution of them jointly, then it becomes a completely different manner, right? The dimension increases, and that makes it a lot more complicated. And let me try to do some of the steps in the solution. So what we have is, let me just make sure I get the notation right here. We have a U. So this here is homework 7, 2, right? So we have a U, which is uniform. So what does it mean to be uniform? That means that the probability that U is less than, say, X, this is equal to X for all X between 0 and 1. Right, so this is the distribution. So that's the terminology, right? This is the distribution. So if you want to get the density, then this is equivalent to saying, in this particular case, we can also say that the U has a density 1, we take the derivative for all X between 0 and 1. Okay, so now we're going to form new random variables. Now we're going to be looking at, so we can do the same thing for X, right? So we said we can do the same thing for, it's not U that's uniform, it's X and Y that are uniform. Sorry. X and Y, they are independent uniforms. So X and Y has density 1. And then we said U to be the product. So then you could ask questions like, what's U's distribution? or density. And you could ask what's u, and then the thing that you ask for is u and x is joint distribution or density. And so maybe we should just revisit quickly how one would go about doing this. So we're going to need, what are we going to need? We're going to need the, if you want to look at the distribution, you're going to look at the distribution, right? So that would be the probability that x is less than x and that u is less than, say, u. What is this equal to? And that's the joint, because you have this comma in here. And so if and when they're not independent, we cannot just take the product. It won't work. We can also ask for the density. So this here is the distribution. If we were asking for the density, then what would we write is, what is the probability that x is less than x and that u is less than little u? Sorry, my phone rang. And now what we want to do is we want to write this here as a double integral. And we're going to be integrating here from, this is the first one, this is my x variable, and then I want to have my u variable. So I'm going to be integrating from minus infinity to x, little x. And then the other one is from, let me just write the same, minus infinity to u. And then I want to put in f of, and then we need a variable that we're integrating with respect to, so let's call it v, let's call it y, and v, and d, and then we're integrating first with respect to the v variable, and then with respect to the y variable. Right, so this one here is the distribution, this one here is the density, f of two variables. And the question is, how do you compute this? Are we good so far?
Yeah, this makes sense.
Right, so now it's a question of executing. So how do we find this function here? And the thing you have to hang your hat on is, you know, something about x and y, right? You were uniforms, and then you also know, that they're independent. Right. So had it been x and y down here, then it would have been a lot easier, because then you would just take the product. But you don't have that. So the complication is, how does one do something like this? So let me see what I tried to do in the solution. Yeah, this was back when we were, so one way to do it is to do this Jacobian trick. If you, so you know that when you do an integral, so if you do integration by substitution, then if you're looking at the probability of, say, g of, let me take g of x, right? This is less than some number x, or maybe you will write it more generally, maybe that'll make it easier, so we don't have all these little x's floating around. But if I say that this is the probability that this takes values in some set a, the way that we would do it is we would write this here as an integral of g of x in a, and then we want to have the density of, so let's say, what should x's density be here? So 1. dx. But then you can do an integration by substitution, right? You can substitute y to be what can you substitute y in to be? Because what you might how would we do this? So you have g of x. I'm trying to determine whether I want this little x here to be over here or not. Right, if I would substitute y to be g of x, then what would you get? You'll get the dy dx. This is equal to g prime of x. And then you will be able to write this here as an integral over y in a. And then you want to have your 1, and then you want to have dx. Dx is going to be equal to dy over g prime of y, g prime of x. And then you want to substitute, you need this thing here to be invertible, so you want to move this to the other side. You're going to get dy inverse of x, and plug it all in over here, and you're going to get your density. What will it be? 1 over g prime of g inverse of y dy. Right, so if your random variable is g of x, then what you want to know is this probability that y is an a, and you want to be able to write p of y less than y. You want to be able to write this here as an integral from minus infinity to y, and now you have the formula over here. And because your a in this particular case will be minus infinity to I shouldn't call it. This is the problem I was running into. I have too many y's, so we call this y0. Then this will be up to y0, and you'll get the density for y. You can read it off as this one in here. So what we have now is more complicated because this here is one-dimensional. What we have is a two-dimensional structure. So you need to know how to do integration by substitution. In our case, it'll be this vector x and u will be given as the formula was x and then x times y. So you need to recognize that what you have here, this is g of x and y. But for which function? Our y up here was a function of g of x, right? And that's what's the key thing that we had to invert. And what you have here, this is the Jacobian, which is the one that we're going to be computing now. So you need to recognize what this g here, what is this g that will take you from x and y's into x and u's. So it'll be g of x and y will be, well, it will be, the first one is just going to give me x, right? And then the next one is just going to give me xy. And so for the Jacobian, well, we also need to inverse it. We need the inverse. This is the same thing as what we have here. We need to do the inverse. So g is inverse. So now I need to be able to solve. I have points. Those are my a, and this is my b. We need g inverse. It just says we needed it up here in the one-dimensional case. So how would one go about solving this? So what is your y? Well, so a is equal to x, b is equal to the product. So we will take this. This here will then be ay is equal to b. And so the inverse is what? inverse is going to be A, and then the other one is going to be what, B divided by A. Does that make sense?
Yeah, that makes sense.
Right, and so now when we do integration by substitution in 2D, then there's going to be, so what's the formula for integration by substitution in 2D? So you need the Jacobian. So the Jacobian is when you compute derivatives of this thing. So we can do the Jacobian, G, and then you have A and B. So now we have to compute derivatives. So first you need the derivative with respect to the first entry. So that's going to be a 1. Then you need the derivative with respect to the second entry. So now A is downstairs. So this is going to become something like minus B over A squared. And then you need derivative with respect to B. So take the derivative of A with respect to B, you're going to get a 0. Take the derivative with respect to B over A with respect to B. This is going to give me 1 over A. And then you do this substitution here for the two-dimensional case. You need the determinant of the Jacobian. And then you take absolute value. Okay, so let's compute the determinant. So it is this thing minus that thing. Right, so it's 1 times 1 over A minus this thing, that's a 0. So this is going to be 1 over A. And then the density when you do this integration by substitution, you're going to get that the density has to form F, so the joint density of X and X times Y evaluated at points A and B. You will be able to express this in terms of the joint density of X and Y, which is easy because that's just a product. And then you compose it with, what is it, the inverse of the Jacobian, no, the inverse of G times the absolute value, 1 over. But this one here is easy, right? This is just 1 over. And this is because X and Y were independent. So this one here, this is equal to 1. And provided that when is the joint density equal to 1, right? So we need to write something here. It's not always equal to 1, right? We will have the probability of X being less than little x, right? This was equal to, let's write it out here. When X is negative, this is equal to 0. When X is between 0 and 1, this is equal to X. When X is strictly bigger than 1, this is equal to 1. Right, so the density for X is going to be the derivative. So Fx evaluated at, say, X, what is that equal to? Well, this will be equal to 0 when X is negative. It will be equal to 1 when X is between 0 and 1. And it will be equal to 0 when X is bigger than 1. And the same thing for Y. Right? X and Y have the same distribution. So these two probabilities are the same. F of Y, X is equal to the same. So provided what? Provided that G inverse of A and B belongs to these intervals here. Right, so what we need here, G inverse of A and B, we computed it, right? This was A over B. This here was A, B divided by A. So we're going to need some bounds here. So what we're going to get is that A, the first variable has to run between 0 and 1. Okay, so A has to be between 0 and 1. The second variable also has to run between 0 and 1. Right, but that we can simplify. This here, this is going to be the same thing as saying that B belongs to 0 to A. right? So that's the density, and then it's 0. You see, as soon as you get outside these intervals, then the formula for the density is going to drop to 0 because you have zeros outside. So it's equal to 1 over a for a between 0 and 1, and for b between 0 and a, right? And then it's equal to 0 else. And you should, of course, always do like some sort of a sanity check. And so we do that too here. Like this thing has to integrate to 1. So if I integrate from 0 to 1, that's where a runs, right? And then b runs from 0 to a. And then I take the density f x y a b dA dB. What should I get? What should this be? What should I get when I integrate the density?
Should it be 1?
Yeah, and is it true then? If I plug all the, like, this is just a sanity check. It's like a checksum. It's something that has to hold. So if I take 1 over, what was it, 1 over a here? And then, oh, I need to, I messed up the order of integration. This is what happens when one is not careful, right? This one here is the b variable. This one here is my b variable. This one here is my a variable. So I did it wrongly, right? This should not be dA dB. This one here should be dB. Right? It's the b variable that runs between 0 and a. So this here is dB and dA. And what do I get? Well, the first integral in here, this is there's no b, so you're just going to get a times 1 over a. This is a 1. And then you're going to get a 1 integrated from 0 to 1 dA. There's no a, so this is always equal to 1. So this has to be true. And the other sanity check is that so I should say sanity checks here. The first one should be that it's positive. If x, y got to be positive, and then the second one is that it has to integrate to 1. But so it requires that this way of doing it, it requires that you have, I mean, you could also, I didn't do this in the solution, but you could also you could attack this, this joint. Where did I write it? Right, this one here, you could attack this here directly and try to work out what these two intervals are. In a solution, I just used the formula for, I use this, how do you substitute when you have a two-dimensional problem? And so the last part it asked about is it true then that x and x times y are independent? And the answer is no. And so one way to see it would be to look at the joint density, which is what you have here, and then is that equal to, so check for independence. So x is independent of x times y if and only if fx xy is equal to fx times fxy. And so in the first part of the question, right, you computed what this one here was, and this one here was given. This is equal to 1 or 0. But you can see there's trouble here. This is not possible because if you look at the domain, you have this weird shape. Like A can run from 0 to 1, but B can only run from 0 to A. So if you plot it, if you so this is not possible. This is not true. And so you can do it by computing this one and checking it, but there's a shortcut here because the way that the domain for this object, this joint density between x and y, the way that it looks like is it has the wrong form. This cannot happen. So let me try to explain this. You would have A and B here, right? So A runs freely. It runs from 0 to 1. And where does B run? Well, B has to be less than A. So if I map out the diagonal here, this is the diagonal. Then what is the domain for this guy? Well, it'll be anything here, and then you can go up to the diagonal, right? So this is where f of x and y is equal to 1 over a. And this is not a rectangle. The domain is not a rectangle. And then you cannot have, you can't have this property, because if I look at what I have up here, this always has a rectangular domain. Because this is just going to be a function of, so this was A and B, this here was A, and this was A. And this one here was B. So this one here has a non-rectangular domain, and this one here has a rectangular domain, so it can't work. Like there's no, when I look at what this object here is, there's no restriction on B in terms of A. And indeed, if you write it out, right, this thing here was equal to, that was in the first part of the question, was it something like minus log of B. And this was for B between 0 and 1, right? There's no weird restriction on what the B's can vary in. Whereas over here, there's a strange restriction that B cannot go above A. So this here has a non-rectangular domain, and this one here will always have it. And so they can never be the same. Did that clarify?
Yeah, this clarifies like a ton.
Can you say that again?
Yeah, this definitely helps.
Yeah. I mean, questions of this sort here, you per se not like so relevant for the class that we are doing, but there are lots of elements in here that are relevant, like independence. This is something we use many times. We're going to use many times today. And working with these densities, this is really, it comes up in 622 and 623. Are there other questions?
Wait, actually, I have another question. When would joint densities come up like in computational finance? Like, can you give an example?
Yep.
Okay, cool.
Yeah. So right. Even if you would think about it just in our class, right? If you would think about our stock price, so you have your S0, this would be our constant. This would be our constant, right? And then you would have your S1, this would be equal to S0 times psi1. And then you would have your S2, this would be equal to S1 times psi2. And so we could ask just what is the joint density? Oh, we don't have a density here because our size are coin flips, right? So we could talk about the joint distribution. The joint distribution of S1 and S2. they're not independent, right? S1 and S2, they are not independent, because what I have here is S0 times psi1 times psi2. So you have exactly this product structure that we're dealing with up here, right? You have your, this could be your psi1, right? And this could be psi1 times psi2. So you have exactly this product structure. So we could ask for, what is the joint distribution here? And these guys, they are not independent. And you would have exactly that this would be S0 psi1 and then S0 times psi1 psi2. So this, the structure that you have here, it's not that different than what you have up here. It's just that when we work with stock prices in a binomial model, the size that we're dealing with, there are conflicts, so there's no density available. But the fundamental problem, namely that you don't have independence, and this is very much there. I mean, and you do want to know things like this, right? You do want to know how the stock price as a process, how does it evolve over time, and does it have like autocorrelation, right? Because these stock prices, because they're not independent, you can compute the covariance, and you're going to get something that is not zero, right? If you looked at the covariance of S1 with S2, you would end up with what? You take the, what would you end up with? You would take S1, so this would be S0 psi1 times S0 psi1 psi2 minus, and then the expectation of the product is 0 psi1 just squeeze it in, right? This is not a zero, because that product you have here is not equal to what you have over here. The expectation of this product here is not equal to the product of the two expectations, exactly because they're not independent. But so we would be interested in how the stock price at time 2 co-varies with the stock price at time 1. And in continuous time, the way that it goes there is that what you put over here is, instead of having psi1 just to be this coin flip, what you put here is going to be something that has a normal distribution. So it's going to be an exponential of a normal.
Okay, awesome. Yeah, this clarified a lot.
Yeah, I mean, you guys, when you have these, when you have questions like this, you're more than welcome to use my office hours, and we can try to get this squared away before the homework is due, and try to get this this eliminated as much as possible. I had posted, but it's been a while. I don't know, maybe a couple of weeks ago before the midterm. I did post like a set of some sample problems on this type of probability questions. So there are some more sample problems out there on Canvas if you want to have more practice. Some of you, so also it was in that connection that some of you asked for, like, what would you recommend in terms of like an elementary textbook that one could use? And let me just show you one. So if you are interested in this, is a pretty easy read. It's and it's also very affordable, so it's not expensive. Spilled coffee on it, so bear with me on that one. So it has a lot of the topics that we've been using, like probability distributions, independent random variables. We've been talking quite a bit about characteristic functions and properties of them. We also have been talking about martingales. So martingales come over here. And so, for instance, if you were to look for this this result that we used, I think it's in here. So we look for the Jacobian, page 92. So if you flip over, so the result that we're using is this one here. That tells you how do you do integration by substitution in more than one dimension, right? So what we're using it for is I think n here is 2 in our case, right? It's something that goes from a two-dimensional to a two-dimensional, right? X and Y, you were one-dimensional objects, and then we formed U, and we considered U together with X. So that was a transformation from R2 to R2. So we do the Jacobian, which is nothing else than just all the derivatives put into a matrix. And then you compute the determinant. When you're in higher dimensions, you need to know how to compute the determinant in higher dimensions. And then the formula we used for the density was what you have here. Right? You take the density of what you know, you compose it in this way, and you're going to get this new density that you were looking for. So that's this result, and you can find that in here, along with, I mean, there are many other. This is just it's a nice reference. It's not very long. It has lots of exercises. It's pretty cheap. It's written by two very, very serious researchers. So it's a really good book. Probability Essentials. All right. Are there other questions before we get started? Okay, if that's not the case, then so should I would you guys prefer that there were a few more of these probability questions on the homework, or what's the general take?
Yeah, I'd say like throw in one.
Okay, I'll put in. Yeah. I'll put in one more on the one that's coming up later this week.
Yeah, I agree. I think it would be helpful though if we had I think I was just a little bit lost during the homework, or while I was doing the homework, because I looked at this and it was kind of the first time I was seeing it, even though I'd seen some previous classes. I think it's a good review though. This is really helpful.
So let's put in another one for next week, and then see if we can get it to work better. And as I said, you are more than welcome to use my office hours and Sherry's office hours to get nudged along on these things. It is, as you guys say, people in this class, they come from various backgrounds. There are students that have recently seen this type of probability. There are students that have seen it, but it has been a while. Then they're just students of all sorts of backgrounds here. So doing some of this review before you actually need it, this is kind of my goal, because you will need this stuff in the spring. So if we can kind of get it reviewed a little bit here in the fall, so you can hit the ground running in the spring, this was my hope. And then and for some of you that are sitting there thinking like this, I just had this in the spring semester, I don't need this, and this is great. But just once you just understand, we have a pretty diverse group of students. With I was talking to one student about it, and we're going to see something very similar when we come into the spring and in 623. There it will also involve a lot of coding. So then we will have students that have a lot of experience in writing software. And then there will be some students that have written software, but it's been a while. And then there are some students that have not written very much software. So there we'll also face a situation like the one here, where students have this quite diverse background, and we somehow have to bring everybody on the same page so we can solve the same set of problems towards the end of the course. So this is just the nature of these master programs. There's nothing wrong or right about it. This is just how it goes. You bring together people that have quite different backgrounds, and then we just have to do this sort of review and work with it as we go along. Okay, so today, so I should say, what are we going to do today? What we're going to do today is we're going to continue on this. We'll split the course time into two. We will look at this change of measure. We started on it last week, and I know this has traditionally been a difficult topic. So we'll be going over it. Some of the stuff that we went over last week, I'll go over it again. So change of measure. So this has been a troublemaker in the past, and so I want to spend some time on it. We need this for this is needed for fixed income, and this is the last. This is chapter 6 in Shreve. And then after the break, we will revert back and do more about American options. I'm going to try to do some more problems. I posted a large set of problems, and let me show you this on the Canvas site. The other day, I pulled together old exam questions that I had given out that would be relevant to this second part of the class, and I put them all up. It ended up being a large batch of problems. There are 50, I forget how many problems, 50 some problems, 54, 57 problems. Those are problems that I've been using at various stages in the past, and lots of them they're relevant for this class. It depends a bit on how long and how far we get, but I'll go through. My plan is to go through a handful of them today and do the same thing for the next lectures. So when we're studying American options, here we will do some of these problems, right? So you should check the new problem set on Canvas. Okay, so let's start with this change of measure. This is in the change of measure material. This is sections 3.1 and 3.2 in Shreve. So for us, when we work in a binomial model, the starting point is always to take the sequence of IID coin flips, Bernoullis. So you go up and you go down, probability P, and then 1 minus P. This is always the starting point. And so the first I, this is the word independent. That's the first one, right? And then the other two is identically distributed. Right, so ID, this is identically distributed. What that means is that this P here, it does not depend upon N. You could conceivably have coin flips where the probabilities depended upon what time period you were in, but not in our standard model. So this is what is happening here. And then we have the independent property, right? And the independent property says that you take what does it say? You take psi1 is in some set A1, psi2 is in some set A2, and the probability that psi-n is in some set AN. This humongous joint probability, right? So that's the word again. These commas here, I wish it was standard, but it's not the standard way to write it. But one should really write this here as an intersection. Like this comma here should really be an intersection. Right, so it's the intersection, the probability of these things happening at the same time. The way to compute that, when you have the independence of these random variables, Well, it's going to be as saying that I take the probability of the first one, and then I multiply. It is this multiplicative nature that leads to the property that if you want to be independent, you can test for the joint density being equal to the product of the marginals. Like it is this product structure that produces this this equivalence. This here turns out to be, I mean, you can work with it. This is fine. This is the definition, but there's a much more operational way of doing that, and that goes through characteristic functions. So this here is completely independent. This is completely equivalent. There's no difference between this property here and then going out and testing that the joint characteristic function, so I, and then let me put in a constant A1 psi 1, all the way down to I A N psi n, that this joint characteristic function, and this again joint, that this has the product structure, that this is equal to the expectation of I A1 psi 1, and then up to the last one. Right, so whether you test this property or you test for this property, this is tomato. These things are equivalent, and it's just this one here. It has turned out to be easier to work with. So we will very often compute the joint characteristic function and see if it has the product structure. And it's if and only if. So if it doesn't have the product structure, if this thing here fails for some A1s and A2s up to ANs, well, then you're not going to be independent. So it's if and only if. This is exactly the same, saying that this here is true. But here the sets capital A's, those are sets. And here the little a's, those are points in R. Okay. So what do? So we change our measure. Let's do an example to get started, just to recall and refresh what we talked about last time, right? So let's do an example. And the starting point is going to be to look at this Black-Scholes type model where you take a random variable, it has mean 0 and variance 1, and it's normally distributed. And then you form a change of measure using the Radon-Nikodym derivative. So what we're going to do is we're going to define. So what does that mean? What does this notation here mean? This means that the probability that x is less than x, this can be written as an integral from -infinity to x of 1 over square root 2 pi e to the minus y squared over 2 dy. Like that, this symbol here on the left, this is what it means for any x in R. So that's the distribution has this particular form. That's what it means to be standard normal, mean 0, variance 1. Okay, so given that guy, that's the p measure, right? So that's the assumption. This is input. We now define a new measure q by saying that q on a set A. Maybe I shouldn't use A. So A over here, these sets are wheels. So here the sets AN, they are inside R, right? And A little n was an element in R. So these are sets. This here is AN. So let me not use A over here. Let me call it something else. Just to avoid confusion. So let me call it E. This is the formula. We're going to take an expectation under that measure P of 1E, and then the Radon-Nikodym derivative is going to be e to the x minus 1/2. Like that's how we're going to define this for any set E inside the sigma algebra that x generates. Right, so we should just do a sanity check. Sanity check, right? Q should be a probability measure, right? So we should have a, if I put in omega, which is always an element in the sigma algebra, I better get 1 here. So what will I get? Well, I'll get the indicator for omega, and then the expectation of x to the minus e to the x minus 1/2, And the indicator for omega, that's everything. So this is just going to be the expectation of e to the x. And then I can take the constant outside and I get this formula. And then we need to remember, when I compute the moment varying function for a normal, what is the expectation of the exponential to a normal? And do we all remember this at this point? Do you all remember what this guy here is?
E to the 1/2.
E to the 1/2, right? So you combine the two and you get the one that you're looking for. So that's a property that any probability measure should have, right? P has the probability, has that property, right? And Q here, the new measure, this is a definition, right? So the new measure also has it. We should also have properties like, if I take E1 and then I take union E2, and now this should be true for any E1, E2 in the sigma algebra that are disjoint. So if I do that, will it hold up? Will it hold? What would that formula be? It will have to be Q of E1 plus Q of E2 if Q is to be a probability measure. And so let's work out what it is. What is the expectation, right? And then I have my indicator of this disjoint union. And then the Radon-Nikodym derivative. Right, this guy here, this guy there, this is the Radon-Nikodym derivative. And it's denoted by dq dp. So this guy here is e to the x minus 1/2. So let's work out what this one here is. Now I have an indicator for a disjoint union. Well, that's exactly the sum. This is where we're going to get the summation from. This is E1 plus E2. And then the Radon-Nikodym derivative. And now we're in business because the expectation of a sum is equal to the sum of the expectations. I get here that this is 1 E1 e to the x minus 1/2 plus e to the x to the minus 1/2, right? And now I use the formula. This here is nothing else than Q of E1 plus Q of E2. So it has all the right properties. This is a legit definition, and this gives us a new measure. And so what I want to ask today is, I have a standard normal x up here, and I want to know what happens to this x. What happens to x's distribution when I switch from P to Q? So I have a new probability measure. I want to know what is x's distribution under Q. That seems like a legit question to ask. I have a random variable. I want to know what is the distribution under under this new measure of the old random variable. Okay, so there's a little lemma that will help me do this. So what we need to do, we need to relate expectations under this measure, EQ of something, with expectations under the P measure. So typically we don't write a P up here. I'll also not do that here. We need to relate how to compute expectations on the one measure with how to compute them under another. And the key, of course, is going to be to use this Radon-Nikodym derivative. So the lemma that's out there is this one. This is some form or shape. This is some form of base rule. We'll return to base rule a little bit later today, but let me just state the lemma. And what it says is that if I want to compute if I want to compute an expectation on the Q of a random variable, so y here is any random variable. So let y be any random variable. Any random variable, I should say here, just to make sure I don't write something that is wrong. I need a little bit of structure on it. What I do need is I need to have that the expectation of the absolute value, and then this dq dp in there. I need this to be finite. Okay, so that's just integrability. This is not something to worry about for us when we're doing coin flips. This thing here is always, and when we have this Gaussian structure, this is just, I need to have this property here to make sure that the expectation is well defined. So given that y be any random variable, then if I compute the expectation on the Q of this random variable, then I can do that simply by multiplying down the random derivative, switching the measure over. So here I'll have a P. So there I have Q, there's no random derivative. Here I have a P, and there is the random derivative. I'll multiply the thing down. Right, and the proof, so just a special case, which is, it's not just a special case, it's like the key step in the general case. This is the key step. If you consider y to have the form 1e, so y can be any random variable. In particular, it can be this indicator. E is a set in the I didn't specify this, but let it be any random variable. E is a set inside omega that is measurable. In this particular case, we can work out the left-hand side, and you can work out the right-hand side. In that case, the expectation of an indicator, well, this is going to be Q of that set, right? Because the expectation of an indicator is just the probability of the set. And if you work out what the right-hand side is, the right-hand side's expectation well, I'll just replace y with its expectation, right? And now you see the link. These two things here, they're the same. These two here are the same. This is by Q's definition. So this is the special case where I'll give the proof. The general case starts here, and then starts taking sums and limits of these sums. I won't take you through this general argument, but I want to use this lemma here to settle that question we originally had in mind. Right? So this here is for a general y, is for a general q. Let's apply this result to answer the question: what is x's distribution on the q? And so how do we compute? How do we determine what the distributions are? Well, we'll use, for example, the moment linear function, or we can use the characteristic function. Either one is good. So let's try to compute the characteristic function. Let's try to compute the characteristic function of x under q. Right, so what would that be? Well, I'll compute an expectation of e to the, say, a, and then x, and I'm interested in it under q. I want to figure out what this is. A here is something in R. I want to figure out what this is, and the way that I'm going to do it is using the lemma. It says if I have an expectation under Q, I can bring that expectation, I can relate that expectation to the expectation under P by multiplying in the random derivative. So I'll do that here. So I'll delete the Q up here, put in the random derivative, and then of course I have to keep the random variable in there. And then I need a formula for the analytical derivative in this particular example was ex minus 1/2, ex minus 1/2. I'll put that in here. E, then you had x here minus 1/2. E x minus 1/2, that was that guy. And then there was e to the ax. What do we do then? Well, what do we do then? Well, we can bring the constant outside. Okay, so I can bring the constant outside, e to the minus 1/2. And then what I have left is a plus 1 inside. E to the a plus 1 on the inside times x. Yeah, and how do we calculate what this one here is? Does anybody remember the formula? Now we are on the p. So what is the moment generating function on the p? E to what?
A plus 1 square.
Yes, times 1/2.
Yeah. Yes.
Okay, so now let's factor out. You see what we have here. There's a minus 1/2 there. Okay, then there's plus 1/2 times a squared plus 1 plus 2a. So you see some stuff cancels out, not a lot, but some of it simplifies, right? You have minus 1/2 plus 1/2, you're going to get e to the 1/2 a squared plus, and now there's an a. So it's different. And does anybody recognize what this is the moment generating function for? So on the Q, what is X's distribution?
It's a normal distribution.
Yeah.
Definitely mean is 0. The
mean is controlled by the linear term, right? The linear term is the mean. So we have this e to the 1/2 a squared. This is the variance. Okay, so let's do a little reminder down here. If I have that x it's not standard normal, it has mean and variance. Has mean mu and variance sigma squared. Then we know that x minus mu over sigma, this is going to be standard normal. Okay, so then we know that the expectation of e to the a and then the standard normal. So this is x minus mu over sigma. We know that this here is equal to e to the 1/2 a squared. And then let's work out what the mess is. This here is equal to what would it be? E to the a divided by sigma of x. That was 1. Then e to the minus, what would the other one be? A, and then mu over sigma. Then we can move it around. We're going to get e to the 1/2 a squared, which is what we had up here. And then this one comes to the other side. This is a mu over sigma. This is equal to the moment generating function for x evaluated at a over sigma. So what should I put in for mu and sigma to make this expression be the same as what I have up here? What should we pick for sigma? What should we pick for mu? How would I get A to be the same as what I have here? I'll probably pick sigma to be equal to 1. Right, when sigma is equal to 1, then I just have A. Right, and then what should mu then be? Well, mu should also be 1. So we're gonna have 1 and 1 here. Whereas like on the P, X was standard normal. So you see, it goes from a 0 mean to a mean 1. Any questions on this? I had this step this year can be really confusing because you're really changing the distribution of the variables by changing the measure. So I had in mind that we should do one more example about this one. So let me. So it's one of the reasons that I got started on creating all these additional problems. So if you flip through to problem number 21, I'm hoping you guys can see my screen. So here's problem 21. 21 says, let's play with the exponential distribution instead. Let's play with the exponential distribution instead. And let's try to do something along the same lines of what we did. So I have exponential distributions, they have only one parameter, right? That's that mu there. Their density is given in terms of a parameter mu, which is a positive coefficient. And let's try to do the same and see what happens when you change the measure from P to Q, but now the underlying distribution is something that's coming from an exponential. So this here's problem number 21, just to get a feeling for it, right? So when you're talking about exponentials, they're positive. So there's no probability of assuming negative values, right? And the density or the distribution, the probability that X is less than X, this is, well, it's 1 minus the probability that X is bigger than X. And this is 1 minus this coefficient e to the minus mu X. And this here is for X, X positive, right? Because the codomain is the positive numbers. Okay, so the first question says, let's just remind ourselves on what is the moment unit function for exponentials. Right, we've been working, I think, exclusively almost with the Gaussian. So let's just, of course, they're going to be a different moment unit function, but let's just compute what it is. So if the formula to begin with it is the same, like A is a real number, and you have to compute this thing. But now, what the result is going to be different, and it's going to depend upon this one coefficient mu. So what we need here is we're going to move. So we integrate over omega is here. So we're going to be integrating over omega. So we're going to start integrating over the values over in the image. So we're going to be integrating now from 0 to infinity. And then we replace the random variable by a dummy. Let's call it X. Right. And then I need the distribution. I need the either I need to write the distribution function. So you can write, some people write it like this. This is my f of X up here. But here you have a density, so I can write this out in a much better form using the density. So this will be f prime of x dx, and f prime for the exponential is not hard to calculate. Compute the derivative with respect to x, and I'm going to get a minus mu down. It'll cancel the other minus, so I get e to this mess here. So the first question says, when is this finite? Well, let's calculate what it is. The problem is, of course, when a is too big. The mu is fine out here. That's not a problem, but you can see the coefficients when I merge the two exponentials, I get a minus mu times x. So you can see there's trouble here when a is too big. Right? When a is too big, this won't work. When a is equal to mu, we get explosion. And so it's not going to make it any better when a is even bigger. But this is equal to plus infinity. And then when it's finite, this is when a is small, smaller than mu. And what do we get here? We have our mu, and then we will divide by a minus mu. So you see, this is quite different. This is quite different from the Gaussian, right? The Gaussian would have the Gaussian would have e to the 1/2 a squared. That was what you got out of it. But over here, you have something that is quite different. You have I feel like I swapped something here. I think I messed up a minus sign. This should not be like that. This should be a minus sign. I missed. You see, the sanity check here is it doesn't work, right? This mu here is given to be positive, but a minus mu, this won't work, right? This is mu is big. So this 0 will be negative. This cannot be the right answer. I messed up a sign. I should have been more careful. But you see, it's mu minus a. This has to be positive because I'm taking the expectation of a positive random variable. So make sure that whatever we get out in the end has the same property as what it should have here in the beginning, namely positivity. Anyway, this mu over mu minus a, this is quite different from what we saw with the Gaussian. And nonetheless, this is the moment function for an exponential. Then the next question says something along the line, I want to change the measure. Okay, and the way that I want to change the measure is by looking at the QDP. I want this to be equal to, I want this thing here to be equal to e to the x, which is very similar to the formula. Very similar to the formula that we had before, right? This was exactly e to the x, and then we had to do a correction, and we needed this correction to get it to be a probability measure. Right? If I hadn't done this correction here, then the probability of omega would not be 1. It would be something else, and we needed that correction term here to make these two things even out and become a 1. So without that correction term, this would not be 1. So now the question is, what is the correction term I have to put here this time? Well, the proposal is to say, let's put in a constant and let's figure out what the constant is. So then we need q of omega to be 1. This is the same as demanding that, this is the same thing as demanding that the expectation of 1 omega times c times e to the x is equal to 1. And our job is, well, 1 omega, this is 1, so we get a constant outside, then I get the expectation of e to the x. I want this to be 1. Well, I just worked hard to figure out what this expectation was. I use this for a. I use this for a equal to 1. I'll get mu divided by mu minus 1. This would be C times mu over mu minus 1. I want this to be 1. And so I solve what C is. C is equal to mu minus 1 over mu. So what I need here is I need mu to be bigger than 1. And so when I have that, I'll get my Radon-Nikodym derivative to be I'll get that to be mu minus 1 over mu times e to the x. That's the Radon-Nikodym derivative that we get in the exponential case, and you can see it's quite, even on one hand it's similar, right? It's e to the x, so that's good. It's e to the x, that's good. And then there's a correction term, and then there's a correction term that's being multiplied on. How does that sound to you guys? Are you with me so far? Are you guys with me so far? Are there any questions? And then the last part of the question is asked, so what is the what is X's density under Q? But we know what X's density was under P. Under P, we took a derivative. We got mu e to the minus mu x. When x is positive, it's 0 otherwise. That's when we compute expectations under P. But now we need to know what it is under Q. What is X's density under Q? Is it still exponential? And so on. So let's try to figure this out. And the way that we could go about doing it would be to compute the momentary function and see what it gives. You could also compute the characteristic function. Let me do the momentary function. But so we're working on the Q. And I have e to what? E to ax. The difference, again, just to highlight it, it looks very similar. The notation is very similar. You have e to the ax, take an expectation, e to the ax, but the difference is I have a q now up here. And down here, there is no q. This is on the p, this up here is on the q. When we do the binomial model, right, we're going to be providing the risk neutral measures, so there'll be a tilde sitting here. Then we write e tilde, we will know what the distribution, we will want to know what the distribution is under these different measures. And so here we want to know what is the distribution of this random variable under that new measure we got ourselves created. That measure is given by this Radon-Nikodym derivative. Let's figure out what the distribution is, and we're using that lemma again. This lemma is what you need, I think, every single time you multiply the Radon-Nikodym derivative inside. You compute the expectation on the P, and then you put in the Radon-Nikodym derivative, and then you keep the random variable. So this step is exactly the same as what we had in the Gaussian case. And now there's a difference, right? We plug in what this guy here is, and that form is going to be different because we're dealing with an exponential random variable. So this coefficient here is different. The method is the same. And you get x, and then e to the ax. So how is this now going to look? You got the coefficient out there, got the coefficient out here, and then you have this thing messed together. We combine the exponentials again. This is going to be e to the a plus 1 of x. And then we use the formula we had derived from the first question. The first question asks us to plug in the formula. Just replace a here by a plus 1. So replace the formula with the mu over mu minus a minus 1. So this here will be mu minus 1 divided by mu times, and then it will be mu divided by mu minus a minus 1. And we can see the mu's cancel out. I get mu minus 1 divided by mu minus a minus 1. So this is very similar, very similar to what we had before. So the density is going to be the density is given by, it would be so it will be what will be, instead of mu, we're going to have mu minus 1. And then we have e to the minus mu minus 1 times x. This is the density under Q is given by that. And this is for x positive. And this is to be contrasted with P. So the density under P, this would be mu e to the minus mu x for x positive. Questions on this? So maybe if you want to test yourself out, so here's here's a problem to try yourself. What would happen if what would happen if I took x independent of y, x and y standard normals, and then I would look at questions like, when is the expectation of e to the theta x y finite? So now I'm doing the product again, and then say for those thetas, define this new measure as e to the theta x y divided by its expectation. We always have to have this normalization constant. All right, so I take the product, take two Gaussians, independent, take the product, define this one, and then what is the joint distribution under this new measure? Is that something we can figure out? Okay, are there any questions either on the problem or on what we've been doing so far today? I just try to think about this problem here, and next time we'll solve it. See if we can get it to work. Like, so the method is going to be the same, but it's going to be more complicated, right? Because there's going to be it's not one-dimensional anymore, right? What we had done in these two previous examples, we had just had a one-dimensional. We only had an x. Now we have again the situation where we have two. Right? So the complication is going to be it's going to be bigger. We're doing products here. We didn't have a product like that before. So this is more complicated. Try to think about it, and then either in the office hours on Friday or next Tuesday, we can talk about how one would go about trying to solve this. Okay, so before we take a break, there is some terminology, and then I have one more problem I want to solve. There is some terminology that one sees a lot when it comes to change of measure. I'm sure at some point I have already used this terminology, but let me write it down. So there's some terminology. So we say Q is so we're going to let P and Q be probability measures. Let's say on F. So we say that Q is, and here's the buzzword, so this is absolutely continuous. Right, so that's the buzzword, absolutely continuous with respect to P if if P of A, P of say F being 0, if that implies that Q of F is 0. Right, so if a set has 0 probability on the one measure, it's going to have 0 probability under the other measure. If that's the case, we say that Q is absolutely continuous with respect to P, and we write Q, and then the symbols are these two less than or equal to, and then P. Likewise, we can swap the roles. Likewise, P is absolutely continuous with respect to Q if the same thing holds, but you swap the roles of P and Q. So if Q of F being 0, if that implies that P of F is 0. And we write P and then these two less than or equal to signs, and then Q. So then the new buzzword here is absolutely continuous. When you have both, so when both P is absolutely continuous with respect to Q and Q is absolutely continuous with respect to P, we call P and Q equivalent. So that's the other buzzword. When you have both the properties 1 and 2, we call P and Q equivalent, and we write, and this is the funny notation, so it's P and then there's a tilde, and then Q. So these are the definitions of absolute continuity and equivalence of probability measures. So the equation that we had before, so for us, what we've been doing is so in these examples that we've seen, we have taken a random variable dq dp. We had him going from omega, and then we had him going over into the non-zeros, such that the expectation of the thing would be 1. Right? Those were our examples, right? And then this was our input, and then what we did was we defined this new measure Q of F simply by saying this was the expectation of the indicator of 1F, and then this dq dp. So you can see here that, so if f satisfies, if f satisfies what? If f satisfies that p of f is 0, right? Here we're computing expectation on the p. So if f satisfies that p of f is 0, well then this one here, the p measure doesn't see this is going to be 0 with probability. The indicator of f is going to be 0 with probability 1. Yeah, because it's so. Then the set over which you take the indicator that has 0 mass. So 1 is going to be the probability of this 1f being equal to 1, that's going to be equal to 0. So q of f. Q of f is going to be 0. So that means, that implies that q is absolutely continuous with respect to p in these examples that we've had. So there's a big theorem called, this is Radon-Nikodym's theorem. It says that if q is absolutely continuous with respect to p, then there exists this dq to p. Then there exists a dq to p satisfying star. So you get, there exists this positive random variable that has expectation 1, satisfying star, and double star. So Radon-Nikodym's theorem says that the example, this structure that we've been working with, this is that's all there is to it. The definition of this absolute continuity property. If you want to have this first one, that your meshes that you're interested in creating, they have the property that the absolutely continuous with respect to p. Well, then they are all given by this form. You can always find a random variable such that double star works, and such that it's a positive and it's a non-negative random variable that has expectation 1. So that's a big result in mesh integration theory. We're not gonna prove that, but so absolutely continuous meshes, they are always given by Radon-Nikodym derivatives. We haven't said anything here about the other way. And so the lemma that will help us there is that so let q be absolutely continuous with respect to p. Then q is equivalent to p if and only if this Radon-Nikodym derivative here, dq dp, is strictly positive. So that the probability of it being strictly positive is equal to 1. So we have a measure which is absolutely continuous with respect to p, then you can get equivalence if the Radon-Nikodym derivative is strictly positive. And you can see why it could fail. You could see, so in the proof, so a key point is to say that, well, what happens if the probability that dq to p is 0, if this one is positive, well then, if I take the set just to be exactly where dq to p is 0, then this set here satisfies that q on the set. What would it be? It would be the expectation of the indicator of f times dq to p. But on that set, the random derivative is 0. So this will be the expectation of 1f times 0. Right, that would be 0. So this is just a key point. This is not the full proof, but you can see why it goes wrong. You will have that there is something has a positive probability of happening under P, but the probability under this measure is going to be 0. So therefore, they cannot be equivalent. You can be 0 under Q without being 0 under P. And so the key thing here is to look for random derivatives that are strictly positive. So, and in all these examples that we have looked at, that is really true. The examples that we looked at, they all satisfy. Like here was 1. This one here is strictly positive, right? It's an exponential, it is strictly positive. And the same thing is true for the Gaussian we had somewhere else. Here was the Gaussian. The same thing was true for the Gaussian, e to the x. This was strictly positive. So it's natural to ask, can you show me an example where this doesn't work? And so what I had in mind was we should do one more problem before the break, and then this is going to give us an example of where it does not work out so neatly. Let me try to bring up the sample problems. Try to bring up the question that I had in mind. We should solve problem number 22. So here we go. It's a mixture of the two examples that we looked at. So we have a random variable which is normally distributed under one measure and it's exponentially distributed under another measure. Okay, so it's exactly a mixture of these two examples that we've been looking at. And then we just want to know, are these measures equivalent? Are they absolutely continuous? Are the what's going on? And yeah, so that's the problem number 22 is digging into this issue about equivalence. So let me try to write some of this down. We have problem number 22. So we have so x is our random variable, and so under P, x is normal.
So we can't see your screen.
Yeah, I'm just copy pasting. I can't keep it all in my head at the same time.
Oh,
Oh, I can do this. So under P, I'm just copy pasting the formulation. So under P, x is normal, standard normal. Under Q, things change. X is exponential. X is exponential. I think the parameter is 1. So the first question is, do we have that P of A being 0? Does that imply that Q of A is 0? But this is the absolute continuity property, right? So do we have that Q is absolutely continuous with respect to P? And if it is, give me the random derivative. So how do we answer something like that? Well, let's see. Let's pretend, right? So if this is the case, if so, well, let's try to find a function. I call the function in the solution for a function z, and it's going to be a function applied to the random variable x, such that dq dp is equal to z of x. Like in these examples we had before, this this z here was an exponential. So can we try to find something? And if we are successful, well, okay. If we are unsuccessful, well, then it probably doesn't work. Let's try to see if we can do this. So if this is the case, then when I compute the probability of, say, x less than x, the way that I will go about doing that, well, this is going to be the expectation, and then I need the random derivative, dq dp, and then indicator for the set when x is less than x. Like that's the formula we're given. Like if you have that property, then the random derivative is going to satisfy this property here. And do we get something that is consistent, or do we get a contradiction? And let's try to work it out. Now we are on the p. So let's try to find that function z here. I take z inside there, and then I run the variable x, indicator x is less than x. I am on the p. Okay, so when I'm on the p, x is standard normal. So what I could do is I could bring the right here I'm computing expectation over omega. I could bring it over into the image over in the codomain, and so I can write this here as an integral over r, and then I replace x with some dummy, I don't know, y, and then one x was replaced by a dummy y. And then what I do is I take the, I need the density now. This was 1 over root 2 pi e to the minus, and then the dummy variable was y squared. So this is y squared divided by 2 dy. Right, so this is if there is such a thing, then that would have to be true. But on the other hand, this one over here, it was stated in the problem that under q it's exponential. So what does that mean? What does that mean? Well, this means that I can get the integral here from, what would it be, minus, so this will be from 0 to x, and then the density. And what was the density for the exponential? This was mu, so this is e to the minus mu, that's a 1, so this is e to the minus y dy. Okay, so can these two things coexist? Is this okay, or is this not okay? Well, let's try. This indicator in here, I could bring that, that's the only place I see an x, right? So I can bring that up here. I can integrate here from minus infinity to x, bring that indicator out here outside, and then out to the integral. And then the function I'm looking for, the density function. So can these two things coexist? Well, it surely looks like the left-hand side, what should the left-hand side be when x is less than 0? Well, then so when x is less than 0, then the left-hand side is going to become a 0, right? But that's not necessarily the case on the right-hand side. Then the left-hand side is equal to 0. And the right-hand side, what is that equal to? Well, it'll be equal to the same thing. If I take x to be, I don't know, -1/2. Let's just try something out, -1/2. Then the left-hand side is going to be 0 because there is no density. The density, the exponential density is 0 around there. And on the right-hand side, you still have something. So you go from minus infinity to, say, -1/2. And then you have your COY, 1 over root 2 pi e to the minus y squared over 2 dy. Right, so for these things to work, what should we have? What should my function z be? Like, I want the left-hand side, of course, to be equal to the right-hand side. For example, at the point -1/2, but it doesn't have to be -1/2, it could be -1, -2, something negative. What should that to make that work, what should my function z then be at such y's? What should c be? How do I get this integral here to be 0? I have freedom in choosing z.
Can we just make z the 0 function?
Yeah, that's when y is negative. Now, what about when x is positive? Well, then the left-hand side becomes what I have here, and the right-hand side becomes what I have here. So I need these things to match up. So when x is positive, we could, for example, take derivatives. So we take a derivative with respect to x of the left-hand side. That will give me e to the minus x, right? Take the derivative of an integral as a function of its upper limit, you just evaluate the integrand at that upper limit, right? And if I do the same thing on the left-hand side, no, sorry, on the right-hand side, the only place that I see x is up here. There's no x in here. So I'll do the same thing. So it'll be c of x times 1 over root 2 pi e to the minus x squared over 2. So what should c, if I want to keep it with a y, what should c of y be when y is positive?
Square root of 2 pi times e to the negative.
So you're moving this one to the other side, right? E to what? E to
The positive x squared plus
yeah.
x squared over 2.
And then we need the pi over there as well. Something like that. And we should always have a sanity check, right? So sanity check. There's nothing wrong with having a sanity check, right? This is a random Nicolam derivative, so I need it to be positive. And you can see here, this when I plug in the Gaussian, so when I plug in x, right, under the measure p, this is normally distributed, so you are going to get down here. But you can see this thing here is positive, right? This root 2 pi and all these other things are positive, right? So this here is positive. We need the expectation to be 1, so we compute the expectation. Is this equal to 1? Because if it's not, then it fails to be a Radon-Nicolam derivative. So how does one compute an expectation? Well, we're under the measure p. So when you're under p, x is Gaussian. Okay, so we'll write this integral here as an integral over r. Then it will be z of x. And then we need x's density under p. So this was 1 over root 2 pi e to the minus x squared over 2 dx. Okay, so c of x, when the input parameter is negative, z is 0. Okay, so I don't have to worry about integrating over r. I can just integrate from 0 to infinity. Okay, what is c of x on that piece? It'll be e to the minus x, e to the 1/2 x squared, root 2 pi. That was the formula for z, right? And then comes the density component. So this is divided by root 2 pi times e to the minus x squared over 2 in dx. And now we see a lot of the stuff cancels out, right? The constants cancel out. This one cancels out. I'm left with the exponential function. And what do we get when I integrate the exponential function? What do we get when I integrate the exponential function? Well, the exponential function is given to be a density. So this here better be 1, right? And those are the properties that the Radon-Nicolam derivative should have. It does. So it's absolutely continuous. But you can see there's trouble, right? This thing here, it drops to 0. This is not greater than 0. This is greater than or equal to 0. So for the second question is asking the opposite, right? So if you have, this was when you had p equal to 0, does it imply that q is equal to 0? So the other way around, if you have q to be 0, if q on a set is 0, does that imply that p of that set is 0? Like, so do we have that p is absolutely continuous with respect to q? If so, provide the Radon-Nicolin derivative. But you can see that there is trouble in paradise here, and the way to look at it, this is when you are negative. So if I look at a set, so the answer here is no. But the answer to the first question was yes. The answer here was yes. And this one here is no. So then we have to cook up a set that does this. So we'll try to take, there are lots of sets you can take, but if you take a set A, this is where you are negative. So if I take a set A where X is negative, then if I'm looking at P of A, well, under A, under P, X was standard normal. So what's the probability of A? If I take a standard normal, I ask what is the probability that a standard normal is negative, what would I get? I look at the density.
It's 1/2.
1/2. And what happens when I look at it on the Q?
Zero.
Right? So we don't have that. Okay. Very good. For us in mathematical finance and in quant finance derivative pricing, you will one place where I think that there are these Radon-Nicolin derivatives that we're working with in let me just turn the camera on. So the Radon-Nicolin derivatives that we work with in quantum finance, they're always going to be strictly positive. So you're going to have equivalence between these pricing measures, and that's why they call equivalent martingale measures, and then the measure P that we start out with. This is why P, the probability of up and down, is always strictly between 0 and 1. Okay, I think it's time to take a short break. Are there any last questions? Otherwise, after the break, I would like to do some more about American options, and then we can continue with this Radon-Nicolin theory next week. Okay, let's take a little short break and then get back on the other Zoom link, and then we'll do a little bit of American options after the break.